And so Hawking said, well, probably that means that the radiation that comes out, it doesn't know. It just how you made the black hole. It just looks effectively thermal, um, and sort of it looks the same
Like
regardless
no
of how you made the
information
black hole.
content
No,
beyond
yeah,
like
no
temperature.
information
Yeah,
contact, just thermal mush.
right.
Um, and
Now, was he
from the
troubled? Was he troubled by that?
Oh, certainly he was troubled. Yeah, I mean, so yeah, I guess not the paper I was just mentioning, but the follow-up one. I think the title was, a breakdown of predictability and gravitational collapse, right? Which, is a fairly alarmist
Yeah,
title, especially by the standards of the 1970s. That was before Twitter. Um,
yeah,
yeah, he was clearly very concerned, right? I mean, he said, look, because predictability, that's what we do as scientists, right? Like the fundamental problem that you have as a scientist is given the state of the system now, what's the state of the system going to be later? That's predictability. And so if that breaks down, then it's like saying science itself has broken down. Or we have to somehow redefine what we mean by science. We need some more permissive notion of science where we can't predict the future from the present. And, I mean, maybe it's true, right? I don't know, anything,
right.
we don't know the final laws of nature, so maybe it's true, but that's not something we should concede easily. That's something that
Right.
we really should take seriously if we're going to give it up.
Now, this breakdown, this loss of information in this process of forming a black hole and then the black hole evaporating away, in a sense, emerged from, as you described to us so nicely, this blending of general relativity and quantum mechanics. So naturally, the supposition is that one of them's got to be wrong or give or something in order to kind of be able to understand what's going on. Hawking famously thought that the the ideas of quantum mechanics might be the problem, right? And
Yes.
so he kind of tried to invent a new version of quantum mechanics that would be amenable to this kind of information loss.
Yeah, so I think it's important to distinguish between quantum mechanics and quantum field theory.
Yep.
So to say that more colloquially, there's quantum mechanics and there's locality. Um, And so if you're willing to give up on locality, then it's not so clear that Hawking's problem is really a problem because maybe the information that's 10 to the 70 light years inside the black hole really can just be non-locally communicated back out into the Hawking radiation. And so if that were true, then quantum mechanics would be fine, right? So quantum mechanics plus gravity could be fine if there's non-locality, if there's major non-locality at play. But then you have but that's I would just say there's really three principles involved, right? There's sort of quantum mechanics or more generally predictability in the sense of what Hawking in Hawking's language, right? Then there's locality, and then there's general relativity. And it's really one of the three that you have to give up. That's
Right.
how I would phrase it. Um, and then Hawking didn't want to give up on locality or general relativity, and so he was sort of forced to, by himself, to argue that maybe predictability or really quantum predictability, sometimes called unitarity, is the thing that has to go. But I think the sort of more modern view, which I guess we'll gradually get into as we go on, is that it's really locality is the thing that goes.
Yeah.
Um,
Yeah, I remember Hawking had a nice slogan. I don't know how widely he used it, perhaps all the time, but he liked to say, not only does God throw dice, but sometimes the dice fall in and get folded and hidden within the crevices of space-time, so their information is gone, so
yeah.
kind of a poetic way of framing it there. So you mentioned locality, and I know we're going to get a little bit further into this, but certainly some in our audience are familiar with ideas that we'll come to as well, these ideas of entanglement, which is a non-local quality of basic quantum mechanics itself, Einstein's
Mhm.
spooky action at a distance. Would pure locality, pure non-locality of quantum entanglement be enough?
No, that wouldn't be enough. And so yeah, so let's try to unpack that a little bit, okay? So let's go back again to this issue of combining quantum mechanics and special relativity, right? So that's the problem that's solved by quantum field theory. Um, And so it's useful to think about how is it solved. Um, so the basic principle of special relativity is that nothing should go faster than light. Um, and when you try to combine quantum mechanics and special relativity to make quantum field theory, um, locality is really the principle that enforces that. Um, so the idea is that, well, I'm not sure where you are. I'll guess you're in New York. I'm in Cambridge.
Yep.
Um, and so right at this moment, you and I are what we call space-like separated, meaning that there's a light travel time between New York and Cambridge, and it's pretty fast. But just moment by moment, we're space-like separated. And so that means that I can't send a signal to you that goes faster than light. And now say that
So you can't affect me
I
instantaneously,
can't
nor can
affect
I
you
affect you. Yep.
instantaneously.
Right.
That's right. And so in quantum field theory, the way that that principle is maintained is that the degrees of freedom I have in my office are completely independent degrees of freedom from the degrees of freedom that you have there. Um, and so whatever I do with them, say I measure them, right? Or I kick them, or I do something with them, it has no effect on the degrees of freedom there where you are, because they're just completely independent. Okay. So that's the kind of locality I'm talking about, independence of degrees of freedom. Now, entanglement is a little bit different. Entanglement is something where you have two sets of independent degrees of freedom, but they can be in a sort of special kind of quantum state. So the configuration of the system can have a sort of surprisingly large amount of correlation between the stuff I have in my office and the stuff you have there. Um, but it's not something that we can use to send information. That's the key point. I can't send signals faster than light. It's just, I have a box with a ball in it and you have a box with a ball in it. And if we open both the boxes, we see the balls are the same colors, but maybe that's just because the balls, we both ordered them from the same seller on Amazon, right? And so then there's a correlation between the balls, but there was no way to communicate between us just using the fact that we got the balls in the same place. Um, Now, quantum entanglement is a situation where the correlation is like even stronger than the kind of correlation we would have from Amazon from buying the balls in the same place. But I would say morally it's the same thing. It's just you can be even a little more correlated in quantum mechanics than you can be just with classical objects, but you still can't communicate using entanglement. Whereas to get out of the black hole information problem, um, you actually need to communicate, right? Like the information of how I made the black hole is there inside. And in order for it to affect the Hawking radiation, the process that produces the Hawking radiation near the horizon of the black hole somehow needs to hear about the state of the state of the matter fields deep inside. Somehow being entangled with them wouldn't be enough. They have to really be talking. You need a telephone.
Yeah. So this seems like a real problem then. I mean, something really has to change.
Something has to change.
And
Yeah.
so I know you weren't around, but in the 70s and 80s, were people going crazy trying to fix this, or was it just kind of a thing out there that kind of people scratch their head about?
It goes through phases. So, I mean, as you know, right, we're theoretical physicists, we think about very hard problems. But, just maybe partly for our own sanity, but I think also as a matter of good science, we want to be doing something where we feel like we're making progress. And so when you have these really big, hard problems like the black hole information problem or the cosmological constant problem, these are decade scale problems. And so to work on them, you need an in. You need some new idea. You need some approach that wasn't tried before, um, or you're just going to be stuck. And so the way it has gone is that every now and then some new idea will come up, and then everybody will go work on the black hole information problem for a while and try to see if we can use that new idea to learn something new. Sometimes we do, sometimes we don't. And then after a little while, it kind of peters out and people say, well, okay, we learned something, but we still didn't solve Hawking's problem. And
Right.
so there were a few iterations of that over the last 50 years, with the most recent one having started back in 2019, I would say.
So I'd love to get there to the most recent one, but I'm wondering if we can get there in stages. And
Yeah.
I mean, you may have a different perspective on it, but sort of a natural next chapter, at least one that certainly had a big impression on me and a lot of others as well, is one that Gerard 't Hooft and Lenny Susskind really were the driving forces behind. Although, frankly, for almost anything, you could say Lenny Susskind was the driving force behind it, and that would be a correct statement. So it
Yeah.
doesn't uniquely pick out this particular work.
But he
But
was
can
my
you?
PhD advisor, so I
Yes, I
can
know
say
that as
anything
well. Yeah.
critical, yes.
So, and so what was the approach that they took to try to at least make some headway on this?
Right. So there's something that we haven't talked so much about in this conversation, but which is very important to the story, which is the idea that black holes have entropy. Um, in fact, that was in some sense what led Hawking towards the
Yeah.
idea of formulating the information problem is that classically in Einstein's theory of gravity, um, a black hole behaves as if the area of its horizon was something like its thermodynamic entropy. Um, it obeys laws that are like the laws of thermodynamics that we learn in high school. Entropy must increase, that energy must be conserved, that temperature is related to the change in entropy over the change in energy. Um, these basic rules of statistical mechanics seem to be satisfied by black holes, but just as a consequence of Einstein's equation, which is kind of mysterious, right? I mean, Einstein's equation is somehow
Wow.
telling you that black holes want to behave thermodynamically, but it's also telling you that they only have they're only labeled by these three numbers, the mass, the charge, and the angular momentum. And there's a real tension between those two statements because usually the whole idea of thermodynamics or statistical mechanics is that you have a big complicated system like an oven or gas or something, and it has many, many microscopic degrees of freedom, and you kind of don't really know what's going on with the microscopic degrees of freedom. You just want to measure, large scale properties of the system, but you can learn things about what to expect by just sort of assuming that the microscopic degrees of freedom are in sort of the most generic state you can think of that's consistent with what you know about the system on the largest scales.
Yeah.
Um, and so somehow, um, general relativity is telling us that black holes should be thermodynamic systems. And as soon as you say that, it's starting to go in the direction of resolving the paradox. Because remember, the problem was you throw something into the black hole and where did the information go? And if we're now saying that the black hole actually has a large number of hidden degrees of freedom that aren't manifest in general relativity, but they're somehow there, then you immediately say, okay, great. Well, that's where the information is of how I made the black hole. It's in those hidden degrees of freedom. And so somehow, if we can just get it out, then we can learn, we can try to make black holes consistent with quantum mechanics.
Wheeler was one of the people who really caused the renaissance of thinking about black holes in the late 60s and 70s. And he worried that if he took, he was a very genteel man. I don't know if you ever met him personally, but he was wonderful. He said, if I have a cup of hot tea and I throw it into a black hole, I seem to have gotten rid of all the disorder, all the entropy of the hot cup of tea. And how could that be? I seem to have violated the second law of thermodynamics. And he gave this puzzle to Jacob Bekenstein, who then realized what you just described. You throw that cup of tea in, the black hole changes. Its surface area grows a little bit, and that surface area is indeed capturing the entropy, the hidden degrees of freedom of a black hole itself.
That's right, exactly. Yeah, and that paper of Bekenstein is really wonderful to read. In some sense, it's more modern than Hawking's paper. Hawking's paper is in some sense better because he computed the number. He computed that
Yeah.
the entropy is the area divided by 4 times Newton's constant. So there's a 4 there that's important to get right. And Hawking also gave the mechanism whereby black holes radiate. But this earlier paper of Bekenstein is really nice because it really makes nicely this case that there are really these hidden degrees of